graph configuration spaces and representation stability.
Great. Well, thank you for having me. So yeah, I'm going to be talking about graph configuration spaces and representation stability. So let's just go on a few basics. So throughout X will denote a topological space, and we will use f sub n of x to denote the ordered configuration space of points in X. So this will be our configuration space, and this ordered configuration space is just the ways of putting n distinct labeled points in X, such that, well, all of the points have different labels because they're distinct, and none of the points have the same location. So these are our spaces, and note that if we act on these spaces by the symmetric group, which we can do by permuting the labels, we can get the unordered configuration space by taking the quotient of this thing. So this is ordered configuration space, ordered configuration space. And if we take the quotient by Sn, as I said, we get unordered configuration space. So this is just the quotient of ordered by unordered. And our main question for today is, well, what happens to these configuration spaces, both unordered and ordered, when we increase the number of points in our configuration space? And well, today we're especially concerned with graphs. And just a quick recall, a graph is a one-dimensional cell complex, and we'll use gamma to denote our graphs, where we're going to call the one cells edges and the zero cells vertices. One cell complex. Edges, one cells, and vertices, zero cells. And for the most part, we're going to be thinking of some of the simplest graphs, namely a subclass of things that we're going to call trees, where we have one zero cell and one central vertex, and k surrounding edges, all leading to their own vertices. So gamma k will denote what we're going to call a star graph on k edges. And this just looks, for example, in 4, well, this is gamma of 4. We've got our one central vertex right in the middle here, and everything else, 4 edges coming out of that. And we want to know, how does the topology of these spaces change as n increases? So the main result that we're going to get to at the end of today is saying, okay, this is going to be nice, but nice in what sense? How does hi of fn gamma k change? And we're going to say, as n increases, what we're going to say is that this is going to be what we're going to call a representation stable. And for me, this is going to mean it's some module over some algebra, and this module is going to be finitely generated. So theorem of mine, H1 of the ordered configuration space of points in the star graph on k edges is representation stable. And as I said, this is going to mean that it's some nice module over some nice algebra. Namely, it's a finitely generated H0 of f dot r k tensor time module. And this is kind of a big chunk here, but what we're going to be able to say is all this means is there are k nice ways of adding points to this graph, and eventually these k nice ways will give us every single class in configuration space. After a while, any new class in configuration space just comes from the classes on fewer points and classes where we add just points at the edge. Things are going to sit there and not interact with the other classes in homology. And so, in order to make sense of this and see why this is kind of expected, and to see, well, where should we go from here, let's talk about representation stability throughout history, or at least since the 1970s. So representation stability, a history. And well, the first of these stability results that we have for configuration spaces dates all the way back to McDuff and Siegel in the late 70s. And it's for manifolds in which the dimension is at least 2 and we're non-compact. And the idea here is that after enough points in our unordered configuration space, we're going to have isomorphisms in homology. So the theorem of McDuff and Siegel is as follows. If X is non-compact and dimension at least 2 and is a manifold, then for all n greater than or equal to 2i, we have some nice isomorphism between the nth unordered configuration space of points in X and the ith homology of the nth plus 1 unordered configuration space of points in X. And this is what we're going to call homological stability, which is kind of the progenitor of all of these results. So this is homological stability. And right, we want to know, how does this homological stability arise? Well, it comes from maps on configuration space that add a particle at infinity. So for example, here's a nice point in the unordered configuration space of 4 points on the ones punctured torus. We have points here over by the handle, 2 points down here, and a third point down here. And this is some point in the unordered configuration space of 4 points on the ones punctured torus. And well, we're going to add a point at infinity by taking this point in configuration space and saying, okay, let's look away from the infinity, or right, the boundary of our manifold, or right, wherever we're talking about, right over here. And we say, okay, let's go back over here, pull the manifold away from the boundary, and add a new point in our unordered configuration space over here. And all of a sudden, we're able to map this point in the ordered configuration space of 4 points into the ordered configuration space, unordered configuration space on 5 points. And well, if we think about it for a second, we can say to ourselves, well, this is also going to induce a nice map on homology. Namely, we can say to ourselves, okay, here's a class in the second homology of the unordered configuration space of 4 points and ones punctured torus. We have this point over here in the handle going around. This traces out a circle. So this is something in first homology. And we're going to take the product with this class down here at the bottom, where these 2 points orbit each other. And so we have another circle down here. And if we think long and hard, this is going to give us an embedded 2 torus in the unordered configuration space on 4 points. And I'm going to claim that this torus actually leads to a non-trivial class in homology. And we can say to ourselves, well, adding this point over here at infinity doesn't really do anything to this class in homology, because these classes doesn't really see what's going off at infinity. So we should be able to say, okay, this is going to give us the same class and unordered configuration space now in homology, second homology on 5 points. And this is going to be the map that gives us this stabilization. And so, right, all we're really doing right here is adding a point at infinity. And so, well, what we say to ourselves is, how do we formalize this a bit more, right? We have this nice isomorphism between homologies when we add a point. Well, we could also say to ourselves, okay, alternatively, the ith homology of the unordered configuration space of points in X can be viewed as a module, namely a free, finitely generated module over the following ring. The ring of the 0th homology of the unordered configuration space of points in R2. And right, how does this thing work over here? Well, right, here's our R2. How do we multiply classes in H0 on any number of points? Well, we can say to ourselves, well, here's a class on 1 point. We add another point over here at infinity. We add another point over here at infinity, and we can see, oh yeah, this is some nice algebra thing that we can actually think of. And this multiplying by adding points at infinity is the same thing that we were doing way up here at the very on the right over here. So we can say to ourselves, oh yeah, we've got some nice module over here. It's free and finitely generated. And moreover, we can say it's going to be finitely generated in degree less than or equal to 2i. And right, that's this condition up here, right, that n was bigger than or equal to 2i. Once we had n points, there were no new classes in homology. Namely, every class in homology that we saw came from a smaller number of points orbiting around each other, and then just points sitting over here at infinity, not interacting with the other points in our configuration or the topology of our manifold. And so we now say to ourselves, great, we have this nice operation on unordered configuration space. Can we say the same thing about ordered configuration space? And well, at first the answer is going to be no. So, right, we can't say almost the exact same thing, but we can say some generalization that works well when we say this module over some algebra thing. So what about the homology of the ordered configuration space of points in X? And right, here's the problem. Say we had 4 points again in our ordered configuration space. And I'll color our points red, blue, green, and orange. So green and orange. And we said to ourselves, well, again, they can make a nice class in the second homology by saying, okay, red goes around the handle, green is going to go around blue, and right, this is some nice class. And well, if we wanted to map this class into the second homology of the ordered configuration space on 5 points, we'd say to ourselves, well, again, let's just add another point off at infinity. And we can do just that. But, right, we run into an issue. We're always kind of forcing ourselves to color this new point over here yellow if we restrict ourselves to only add a new point at infinity in the way that we've already done, right? We can't all of a sudden, in this nice way, go to this ordered configuration space and say, okay, what if I really wanted to add our new point and call it blue and have red do the same thing, but now we're going to swap the role of blue and yellow. And so we can say to ourselves, well, this is kind of an issue, but if we consider the symmetric group action on these ordered configuration spaces, life isn't so bad. We're able to say, okay, if we let the symmetric group act on these homologies and these spaces, the world actually ends up looking all nice and rosy, just like it did with unordered configuration spaces. And it's a theorem of Church, Ellenberg, and Farb, that if you do this and consider the twisting by the symmetric group action, you get almost the exact same result as McDuff-Siegel in this module over an algebra sense. So it's a theorem of Church, Ellenberg, Farb in the oriented case, and this is 2014, and this was extended to all manifolds by Miller and Wilson, that if X is connected, non-compact, finite type, so right, doesn't have an infinite number of genus or things like that, or punctures, and dimension at least 2 again, then for all the ith homology of the ordered configuration space of points in X is a free, finitely generated H0 of the ordered configuration space of points in R2 module. And this is going to be generated in degree at most 2i. So, right, this result very similar to McDuff-Siegel's, and right, we're saying that, okay, any class in homology on more than 2 endpoints comes from a class on 2 endpoints where we keep on adding points in configuration space, but now we allow for some twisting by the symmetric group action to relabel our points and get everything. Is a free finitely generated. I'm going to add the word twisted here just to remind us that SNX. So, right, twisted for this SN action. And so now we say, okay, these are kind of the classical things. We know, okay, in both these cases, we were looking at manifolds of dimension at least 2. And now we say to ourselves, well, what happens in manifolds of dimension 1? Well, in manifolds of dimension 1, we're only looking at the line and the circle, and we say that's a little bit limited. But right, graphs aren't so far off that, especially if we only consider graphs where we have finitely many cells, right? This is a finite cellular complex, not too bizarre. Can we say anything more? And so we ask ourselves, can we get some form of representation stability for unordered configuration, homological stability for unordered configuration spaces, and some form of this representation stability, this Church-Ellenberg-Farb result, for ordered configuration spaces? And I'm going to say for graphs, for this unordered case, it's not so bad, but it's much more nuanced than this ordered case in a certain sense. So for graphs, we ask ourselves, what can we do? Well, we run into one problem immediately. Namely, 1 infinity isn't enough. So 1 infinity isn't enough. And what do I mean by this? Well, in the case of manifolds, if we go back over here and changed our manifold from being the once punctured torus over here to now the twice punctured torus, it really wouldn't matter if I added my new points at this left puncture or the right puncture. In the end, we would get the same thing, up to having to possibly rename our homology classes. We'd still get all of our homology classes in the correct degree, and adding in at the left and the right doesn't really make too much of a difference. On the other hand, with graphs, I'm going to claim this isn't the case. So we're going to look at what we're going to call the most fundamental class in homology, and that's something we're going to call a star. So consider the following picture in the second homology, in the second unordered configuration space of points in this star on 3 edges. So we've got a class, we've got 2 points sitting here and here on the right edge and the bottom edge. And we're going to say that this point on the right edge moves smoothly along the right edge, goes to the central vertex, and now moves to the left edge over here. Now on the bottom, the particle on the bottom edge is going to move smoothly up that edge and onto the right edge over here. Sorry, what was I going to say? Sorry. Now move smoothly up the right edge over here. And on this third leg of our triangle, right, the particle at the top left moves slowly down the edge and finally gets to the bottom edge over here. And this class is what we're going to call a star class. And well, I'm going to claim the following. If we look at this star class in H1 of the unordered configuration space of the star on 3 edges, there are 3 different ways of adding a new particle in a kind of obvious sense. Either at the top of the left edge, the top of the right edge, or the bottom of the bottom edge. And all 3 of those things are going to be different. So, right, we have 3 classes here, adding things at the top right, adding things at the top left, and adding things at the bottom. And well, it turns out that none of these things are the same class in H1 of the unordered configuration space on the star on 3 edges. So we have these star classes and we say, this is not enough. Well, it turns out that if we took all of these possible options, we would actually have everything. And we said, okay, there are 3 infinities in this case. We're able to get every single class in first homology. And well, it turns out, well, most graphs don't have this nice picture where we can add 3 things at infinity in every case, right? We could say to ourselves, well, what about this lollipop graph? So example, lollipop graph. Well, it's not super easy. We only have 1 infinity to add over here. I'm going to claim adding points at this bottom infinity isn't enough. We're not going to get all the classes. So can't get all classes by adding at bottom. But if we allow ourselves to add on all possible edges, we actually can. So we say, okay, these edges that are just leafs where we only have a single vertex and one edge going into that vertex, we don't want to limit ourselves to just that. We want to consider every single possible edge that can be. And so we're going to say add particles, allow us to add particles on every edge. Allow addition of particles on every edge. And right, this is possible because we're dealing with unordered configuration space. Say we had a single particle over here. Well, we can add a particle onto this edge by saying, okay, just kind of put run right next to it. It doesn't matter what side you do it on because, well, the particles look the same. They're kind of like pool balls where if you've got a bunch of red pool balls and you hit one red ball into another, it really doesn't matter what happens. If one goes in the hole, it makes no difference to you. They're not like billiards balls where the numbering on them actually matters. So we can say to ourselves, okay, we allow this possibility. We now can add particles wherever we want. And it turns out if we do this, we're going to get basically what we want. So we get the following theorem of on Drummond, Cole, and Ben Knutson that says, okay, for all I and for all graphs gamma, the ith homology of the unordered configuration space of particles in gamma is finitely presented module over the zeroth homology of the unordered configuration space on R. So right, R is basically just like an edge, but we now need to take a tensor product of the edge number of copies of these things because right, we need to be able to introduce particles at every single edge. And right, sometimes this is overkill, but often this isn't, and we actually need to be able to do this. And so, right, one thing to note here in this result, it's merely finitely presented, not free and finitely generated. Adding particles, so right, finitely presented, right, means adding particles can actually introduce relations. So adding particles may introduce relations. But right, you only have to introduce so many relations. After a while, every single relation in homology is going to arise from a relation on that same homology, that same ith homology on fewer points, where now we've just added a particle that sits there and doesn't really do anything or kind of plays the role of a billiard ball, pool ball being struck into another pool ball. And right, we forget which one is which. The world is a happy place. And right, it turns out that the proof of this result is actually relatively straightforward. And so proof, we can say, okay, the zeroth homology of the unordered configuration space of particles on R with the E-fold tensor product is actually the same algebra as Z adjoin E, where E is just the formal set of edges in our things. And so, right, this is right, just the same thing as X1 all the way through X E. And right, one thing to note about this ring over here is this is Noetherian. So Noetherian. And we say to ourselves, well, how does this help us? Well, it turns out that this unordered configuration space, or rather the ith homology of this unordered configuration space, is really the same thing as the ith homology of something that we're going to call the Siwakovsky complex of gamma. And this turns out to be some nice bi-graded, finitely generated chain complex over Z adjoin E. And what does this mean for us? Well, because the thing that we're taking the homology of is this nice chain complex over some Noetherian ring, it turns out that taking the homology, or right, some quotient of this space, where in this space, this complex turns out to be very nice, is going to result in some finitely generated module over Z adjoin E. And it turns out finite generation over some Noetherian ring is actually the same thing as finite presentation. So, right, we get their nice result just by noting Z adjoin E is a really nice ring, and there's a really nice way of modeling this configuration space into terms of some chain complex. And so we say to ourselves, great, this should do all of our problems now for unordered configuration space. But it turns out that that's not quite the case. So question, right, what about ordered configuration space? What about the ith homology of the ordered configuration space of gamma? And well, we run into two distinct problems. Problem one is that, well, order matters. So, right, problem one, order matters. So no good way of adding particles at every edge, right? We can do this, but if we have some particle traveling along an edge, well, you can't just put a particle right in the middle of that because the particle is going to hit and that start moving. But right, if I shoot a billiard ball, my cue ball, and I hit the 7 ball and the 7 ball bumps into the 8 ball and I pocket the 8 ball too early, right, I've just lost the game. We don't want to do that. So, right, we run into that issue and we say, okay, let's pull back for a second and not consider all graphs because we kind of run into that issue. And the other issue relates to the proof of the Andrum Cole Knudsen result. And that's, well, if we look at the twisted algebra, that's the homology of the ordered configuration space of points in a line, and take the E-fold copy of this, well, this is not Noetherian. And so we can't just run their proof straight through. This proof doesn't work anymore. Sure, you have a nice analog of this Cywikowski complex, but because because it's not a module over something that's Noetherian in a nice way, right, we're not going to get the same results. And so we have to say, okay, what can we do about this? And so our solution to this problem is kind of twofold, right? So solution, we're going to first restrict ourselves to just the star graphs. And first of all, this is nice because we have an obvious way of adding particles right at the edges. So we're going to think about gamma k, and we're just going to say add particles at ends of edges. And so that's nice. And it turns out that these star graphs are actually going to play a very important role in the unordered configuration space as well. And we're going to see thinking about these things is actually the natural first step we're going to do. And right, the second thing we're going to start doing is start calculating. So start calculating and hope you notice some patterns. And so, right, I'm just going to restate my theorem again and see, okay, why are we thinking this, right? And what does our two hints kind of do for us? So theorem, me24, H1 of the ordered configuration space of points in the star graph is finitely generated as an H0 of the ordered configuration space of points in the line module, where we take k copies of this. And right, moreover, we can get a generation degree, generated in degree n equals 4, 3, and 2. And 4 is when k is equal to 3. 3 is when k is equal to 4. and 2 is when k is greater than 5. And right, one thing to note here, why are we focusing on H1? Well, it turns out that these star graphs only have 0th and first homology, and the 0th homology is just the space is connected, so we say to ourselves, oh yeah, everything nice we'd want to believe be true is true. So right, let's worry about the first homology, the only interesting thing that can happen. And right, this result says no new classes for large n. So no new classes for large n. And right, large doesn't even mean that big, right? Large is just 5, 4, and 3 for large n. And right, how do we go about doing this? Well, we say to ourselves, okay, on Drummond-Cole's result, this edge stability that they have up here actually is part of a program they were developing for the homology of unordered configuration spaces. And they wanted to figure out how fast the ith homology grew. And as part of their results, they said, okay, we have the following theorem. The star classes, the things that happen when you have two particles kind of making a circle or doing a 3-point turn around a central vertex, well, those are actually all of the classes in homology asymptotically. On Drummond, Cole, Knudsen. And this is a result in 2022, and says products of star classes are 100% of HI of the unordered configuration space of particles in gamma as n goes off to infinity. And so some things to note over here. How do we take a product? Well, what we can say is, okay, here's a graph, and right in this graph, I can see two subgraphs, namely this star on 3 edges over here, and this star on 3 edges over here. They're disjoint, so we might as well be able to say to ourselves, okay, let's take a star class over here and a star class over here. This is going to yield us some class in the second homology of the unordered configuration space of this H graph over here. And right, this is just an asymptotic result, this 100%. There are other classes in homology, but the only classes that really drive the growth of homology are the products of these star classes. And so we say to ourselves, well, what percent of the classes in these ordered configuration spaces are star classes? And so we go ahead and start counting. So star classes in the first homology of the ordered configuration space of endpoints on gamma of 3. And right, we're going to think about 3 because this is the simplest graph. And right, we can embed this 3-star graph into any other k-star graph because, well, we're insisting that we have at least 3 edges, because if we have the star on 2 edges, that's just the line, and then you have just the line, and that's pretty well understood. And so, right, let's get the following table. We have n, this is going to be our number of points. We have the number of star classes, and we have the rank of the first homology of the ordered configuration space of endpoints in the 3-star. And right, well, the first time these star classes pop into existence is going to be when n is equal to 2. In this case, right, we have 1 star class and 1 class in homology. And right, we're good to go. We say, oh yeah, the star class is everything. Hopefully this continues. And well, you can continue this calculation and say, okay, when you have 3 points, you can say, how many star classes do you get? Well, you have 3 ways for choosing the 2 classes, the 2 points to make up the star, and then 3 ways to choose where that other labeled vertex, that other labeled point goes. And so, right, we have 9 classes in homology. But wait, all of a sudden we can say, okay, now we have 13 classes in the first homology over here. But right, maybe this is just some weird miscalculation. Maybe these classes die off. We don't quite know. But if we continue on in this thing, we can say, okay, it turns out that there are 72 star classes when we have 4 particles. And right, there turns out to be the rank of homology is 121. When there are 5 particles, you have 600 star classes, and the rank of first homology is 1081. And right, we continue on with this trend, and we see that for general n, there's going to be n factorial over 2 star classes times n choose 2. And well, over here, there's a nice formula for the rank, due all the way to Grist in the early 2000s, that says that the rank of the first homology of the star graph is going to be 1 plus n minus 2 times n plus 1 factorial over 2. And right, we stare at this calculation for a second and we say, oh no, star classes are only half of homology, are only 1/2 of homology. And so, right, we can say to ourselves, we need to start calculating more things, right, in order to this be true. And we say, okay, well, what happens when we start calculating? Well, when n equals 3, we needed to add 13 minus 9 equals 4 classes. And if we keep on doing this addition thing, we could say, okay, when n equals 4, we have 121 classes. We knew 72 of those are going to be stars. And of the 4 classes we added when we had 3 particles, right, there are 4 ways to get those classes. There are 4 ways to choose particles to add to them, to choose the 3 particles that are going to make them up. And then that 4th particle can be added in 3 different places. So, right, we're going to have 4 times 4 times 3, or 48 more classes. And we say, okay, we're going to get 48 classes over here. And this is going to leave 1 class left over. So we now need to add 1 class when n is equal to 4. And well, when n equals 5, we actually have enough. But right, how do we know that we have enough? Right, I've said, okay, I can give you a list of more than this 1,081 classes. But right, how do I know there's not some relation between them? And in order to do this, we say, okay, let's actually turn to a spectral sequence to do this. So right, we want to prove we get everything. And I'm also going to put an asterisk over here on this 1 because I'm lying already, in that we're actually going to have a relation on these classes over here, and we're actually going to need to add more than 1 class when we have 4 particles. So right, we can say to ourselves, okay, what do? Well, we turn to the Meyer-Vietoris spectral sequence. Vietoris spectral sequence. And right, we say, okay, if U sub I is some open cover of Y, then the first page of the spectral sequence, the pqth entry is going to be denote a direct sum over all possible p plus 1 tuples of these open sets ui, and we're going to take the pth homology of that. So right, we take the qth homology of that, and we consider all of these p intersections of these p plus 1 tuples u sub I. And this is going to converge to the hp plus qth homology of y. And so, right, for us, our y is going to be equal to the ordered configuration space of n plus 1 particles on gamma k. And right, what we're going to do is going to cover this with u sub j, which is going to be equal to n plus 1 times k copies of f sub n of gamma k. And right, what are these n plus 1 times k copies doing? Well, we're choosing one of the n plus 1 particles to be fixed as the outermost particle on one of the k edges. Since we have n plus 1 particles to choose one of and k edges to choose, we're going to get that many copies over here. And we want to be able to say to ourselves, right, when do all of the classes coming from these things, so right, when do classes in the direct sum of the zeroth homology, direct sum of the first homology of these use of I zeros generate all of the first homology of the ordered configuration space of n+1 points in gamma k. And right, what we're really asking is saying is when is all homology controlled by the E1, right? When is homology controlled by the E1, 0, 1 entry of the sequence? And right, well, we think to ourselves, right, what does this spectral sequence look like? Well, we've got some stuff over here. We've got E1, 0, 0, E1, 0, 1, and E1, 1, 0. And right, if everything is generated in this top entry, well, we can say to ourselves, the only way anything could be interesting happens is, well, when we say, okay, let's go to the E2 page, if this E2 page of 1, 0 is equal to 0, then everything happens in this E1, 0, 1 entry, happens here. And so, right, what is here? That's here. Happens over here. And so we want to determine when is the E1, 0 entry going to be equal to 0? And well, it turns out proposition, well, we can show that E2, 1, 0, where we're looking at the Meyer-Viator spectral sequence for the ordered configuration space of n+1 particles in the graph gamma k. This is going to be 0 for all n such that, right, n is bigger than or equal to 4, 3, and 2, where k is equal to 3, k is equal to 4, and k is greater than or equal to 5. And so, right, this tells us, okay, our theorem is good. Theorem, check mark, right? We can say, going back up to our theorem up here, we now know that the first homology of the ordered configuration space of particles in the star graph gamma k is going to be finitely generated as a module where we're just adding points at the ends of our edges, and we know which generation degree. We can say when k is equal to 3, once we have 4 particles, we have everything. When k is equal to 4, once we have 3 particles, we have everything, and when k is equal to 5, we have 2 particles, we have everything. And so, right, this is already different than the Andrum and Cole result, which says, okay, it turns out with star graphs, you have everything with 2 particles. So now all of a sudden with our simpler star graphs, we get more classes that we weren't expecting. The other thing that we can ask ourselves, question, is right, all of our representation, stability, homological stability, edge stability results said something was either a free finitely generated module or a finitely presented module. And right, all we have at the moment is finite generation. We want to say, okay, what's the next step in any resolution? Can we get some finite resolution of length 2 that will give us something? And so, right, what about presentation degree? And right, this is the question, alternatively, when do we stop getting new relations? And well, it turns out that we actually stop getting new relations fairly quickly. So another theorem is that, okay, the first homology of the ordered configuration space of particles in the star graph on k edges is going to be finitely presented as a 0th homology of the ordered configuration space of points in the line with a k-fold tensor product module. And we can say, moreover, presented in degree n less than or equal to 5 for n is for k is equal to 4 and 5, and 3 for k is greater than or equal to 3. And right, it turns out that this 3 is most definitely sharp for k, for k greater than or equal to 5, greater than or equal to 6. This k down here, this is definitely a sharp bound. This might not be a sharp bound, but if you stare at a nice enough model for this configuration space and you put it into Sage, you could probably get a nice sharp bound. I think 5 is probably sharp for 4, and 5 you could do a little bit better and change this to a 4 when you have 5 edges of your graph. And so, right, one thing to note over here. Well, I haven't talked about k is equal to 3 at all. So, right, what about k equals to 3, right? We know that this ordered configuration space is going to be finitely presented in degree 4, finitely generated in degree 4. That means, right, if we have 4 particles, we can describe every single class in homology as a class from happening on those 4 particles. And well, something can happen off at the ends of our graph, but those particles are just going to be sitting there. We get every single class in homology where things just sit there, and only 4 particles really need to do anything to describe all of our classes. But we're now asking, well, on this star graph on 3 edges, right, do we keep on getting relations? And it turns out that the answer is yes. And this is kind of this weird eldritch horror that says, okay, the first homology, so theorem of mine, the first homology of the ordered configuration space of particles in the star graph on 3 edges, so the thing that looks like a Y, this is not finitely presentable as H0 F ordered configuration space of points on the line times for 3 copies module. So, right, this implies new relations for arbitrarily large n. And so, right, unlike the Andrum and Cole-Knudsen result, we can say, okay, we might start quotienting out with star classes later on, and things could kind of go weird. So we need to keep our heads up and say, if we want some nice thing to be true for all of homology for ordered configuration space for all graphs, we now need to be able to make sure that these classes on these stars are well behaved if they're going to make up everything, and we don't quotient out too much stuff later on. And so with that, I'm done.
Do you have any questions?
I think there's a question in the chat.
So the Andrum and Cole result is true for all graphs. We can say to ourselves, any single graph, almost everything is going to be coming from a star class, right? You might get some vestigial things, and right, we can think of this in the simplest case where we have the lollipop graph, and it turns out, right, you could think, oh yeah, we could just have a bunch of particles going in a circle around a lollipop, sorry, I'm trying to mic. But it turns out all of these classes could be rewritten as things that are, we have a star down here at the bottom and particles just sitting up here. So there's a nice lollipop relation that Andrum and Cole state that says, okay, as long as you have this kind of loop in your graph, you really can replace it locally with a star down here and a few things up here, but nothing really interesting happens when you go around the loop in this graph. Almost everything interesting happening is happening at this vertex at the bottom.
Can I ask a question? As you let the number of strands increase in what you've got. You've got different representations of the symmetric groups, and does your stability result imply, for instance, that the number of irreducible summands in characteristic 0 remains constant from some point onwards, or that indeed that the representations are related in some way, such as by padding the first row? Is there actual reduction?
So yes, so right, you're kind of getting at the Church-Ellenberg-Farb result is known as representation stability because eventually you're just padding the first row of the Young diagram. My result is similar. It tells you, okay, you know exactly how the growth is going to happen, but now because we have these relations in homology, it turns out we're going to be quotienting out some classes and we're merely getting an upper bound. The other thing that I'm going to say that kind of makes this question mute is, well, it's a theorem. So theorem of, I'm forgetting who. It's a theorem of Lugetman that you actually can decompose. So theorem Lugetman, and it turns out that H1 of the ordered configuration space of the star graph gamma k turns out to be one copy of the trivial representation. So the trivial representation and some polynomial number of regular representations of n. And this polynomial is known. So my result is strictly weaker than this result in that we don't actually get this nice formula for the number of representations. We do get an upper bound, and it turns out in proving this and looking at the spectral sequence over here, you actually get pictures for all of the generators and all of the relations if you're willing to stare at them long enough. So now you can start thinking of embedding these star graphs into other larger graphs and saying, okay, what can happen? What do we know? Because the larger project is to say, okay, let's figure out a hopefully finite set of generators for homology for all graphs. You'd hope that most of the things come from stars. And so this is the first place to start.
Could I ask also, you have this algebra over which everything is a module, this non-Noetherian algebra. And but basically, in short, my question is, do you think of that algebra in terms of some sort of combinatorial description? But then when I say some sort of combinatorial description, your algebra is a fairly sort of straightforward combinatorial object, I think. But what I'm thinking of is in Fi, you have a category which is described in a very short number of words combinatorially. Do you have some sort of description in your case?
So yeah, so in my case, actually in the way I write this paper, so the Church-Ellenberg-Farb result uses the category Fi, which is the category of finite sets and injections. And in my case, I use a category that I call FIDO. So again, we have finite sets. We have injections. And for those of you familiar, this is much like something that Eric Ramos described, where we now have a decoloring of the complement of the image. And now, instead of just having a decoloring, which is what Ramos did, we also insist on a ordering O for each color. And so, right, the ordering is corresponding to saying one particle is farthest out from the is closest to the edge of the farthest at the leaf that's farthest out, and right, we're just ordering them along. The coloring corresponds to which edge we're putting them at. And so, right, in my paper, I describe this category FIDO in some detail. I don't actually prove too many results directly about it because it's not too important. But I do show that it's non-Noetherian, and I do also show how the growth of free modules in this category and how they grow in terms of symmetric group representations. It's just something that, to me, knowing this result of Lewis-Getman wasn't too important, but knowing that this is the right category because we need to calculate, well, where can we put our particles, the D, and the ordering of them, right? This is the presumably correct category because, well, in Fi, you don't really need to care about where you put them because all infinities are the same, so no D. And R2, well, I can just move one particle past another, so we don't need to worry about an ordering. Well, with R1, we do. So in theory,
Thank you, yeah.
Do we have any other comments or questions?
I have a question to the earlier part where you reminded us about the results of Macbeth and Siegel and interpreted Eden at a point at infinity as Eden points in the configuration space of points on R2. But I'm surprised it's R2. Wouldn't it be rather the annulus or the function plane?
So it turns out we don't want to worry about adding at the annulus because it turns out, I guess I'll scroll down over here, way to the bottom. Say if we again go to this thing over here, well, the class where this one particle goes around our puncture, that's trivial in homology. So we don't need to consider what happens by that. And so you might as well deal with something similar, which is just the plane in the end. And it turns out that if you know Cn of R2, you also know Cn of R2 minus a point as well. So this is good enough.
I see. Yeah, of course, it's simpler.
It's simpler. There are nice results that actually describe this as an algebra entirely. We're now actually, sorry, this is an algebra where we're both allowing the number of particles to change and we're allowing the homological degree to change as well.
Okay, thank you.
Yeah.
Any other questions? Well, let's thank Nicholas again. All right, thanks so much.
Thank you for having me.